Okay, so let's start. I think there was, I took this, yeah, I think it's from you. So, last section, I explained three things that can be done by the second layer, data link layer. Okay, okay, start here. Okay, number one, I told you I told you last time, data link layer, we can do framing. So I explained what is framing. Okay, this is number one. We can do error control. We can do flow control. And now today, I'm going to explain one of the things, one of the most important things done by the second layer, which is, we call it multiple access, or we call it medium access control. We call it medium access control, or we call it MAC. So this is one of the very important things done by the second layer. Okay. So what is medium access control? Okay. So I'm going to tell you, in some networks, like for example, in case of bus, if in this LAN, in this LAN, we have a shared bus. Okay. So in many situations, we have shared medium, transmission medium, communication medium. We have shared medium, shared. Okay. So for example, we have a cable here to connect these computers together. This cable is shared. So shared means if you transmit, everybody can listen, because this is shared between all of us. There is another case in case of Wi-Fi. So in case of Wi-Fi, all of us share the air. So if I transmit any data, all of us, you can listen to this data. Okay. This is what we call shared medium. So anybody here doesn't understand what I mean by shared medium? Shared medium. So there is no dedicated medium between every two computers. There is no dedicated medium. This is a shared medium between all of us, shared. And because of the share, if you transmit any data, everybody can listen to this data. Okay. As we see. Any questions? Okay. One more thing. To use the shared medium, because we have shared medium here, to use it, there are two different ways. One way, as I explained before, this medium has a certain bandwidth. I can divide the bandwidth into bands, as I explained before. And every computer can use different bands. That means we can have multiple transmissions at the same time. This is one way. So one way to share the medium, everybody's going to have a certain frequency range, and then all of us can transmit at the same time. It's okay, right? Because we are using different frequencies. So this should be okay. It can be done this way. There is another way. The other way is you can take the whole. So if you want to transmit, you can take the whole bandwidth during your transmission. But in this case, so here multiple transmission. Okay, here I mean multiple transmission at the same time, simultaneously. But here it's not multiple transmission at the same time. Okay, what happens here? Only one computer can use the medium. Only one. Okay, but when you use the medium, you can use the whole bandwidth. Okay, when I say you use the whole bandwidth, that means you are going to have very high bit rate, as I explained to you before. Here you are going to transmit all the time, but you have a small bit rate. You can transmit all the time, but you have a small bit rate. Okay, any questions? The problem here, if I allow only one computer to transmit at a certain time, and you can use the whole bandwidth of the cable, in this case, if two computers are transmit at the same time, using the same frequency in the same time, that's what we call collision. Again, don't be confused here. What I'm saying is that here multiple transmissions are okay. Here multiple transmissions. Why? There is no collision here because we use different frequencies. But here's a problem here when there are more than there are more than one transmission, and all of us transmit at the same time using the same frequency band. So collision happens. So what is the meaning of, what do you mean by collision? Is that a bad thing or good thing or whatever? No, collision means you transmit data and I transmit data at the same time, okay? Our signals are distorted, got distorted. You add a voltage, I add a voltage. So the signal is distorted. So my data are not going to be delivered, your data are not going to be delivered. So it's lose-lose situation, right? No one used this channel. We lost the channel. You didn't use it, you didn't use it, the channel, also I didn't use the channel because the signal got corrupted because of the multiple transmissions. You understand what I'm saying? So for sure, collision is a very bad thing because we are using the channel, we're not using the channel, we lost it. Got what I'm saying? So how can we avoid this problem in this case? I'm talking about this case, okay? Here, we don't have collision here because everybody has a certain band. I'm not going to allow two computers to transmit in the same band, okay? So we don't have collision. But here we have collision. Why? Because two computers can transmit in the same frequency band. Got what I'm saying? So for sure, so collision is a bad thing. It's a waste of resources. It's a waste of the channel, okay? So how can we avoid this one? That's what we need a protocol for that. Very simple. We need coordination. We need to agree with each other. We need to coordinate to avoid, to reduce the chance, or if we can eliminate, I will be happy if we can eliminate collision, or at least we can reduce the chance of having collision. Is that okay? So to do that, we need some kind of coordination. We need to coordinate it, right? Somehow. That's what we need a protocol for that. This protocol, we call it medium access control. So the medium access control protocol is actually should determine who can use the channel medium and when. So we need a protocol to determine who can use the channel medium and when to reduce or eliminate collisions. Is that okay? So here, that's what I'm saying. Let me read what I said, what I wrote here. Multiple users can communicate by broadcasting into a shared medium. A single shared broadcast medium. That means all computer can receive data because this is a shared medium. Okay? Collision happens, so actually bandwidth is wasted. So we wasted bandwidth, okay? So no one is gonna gain benefit from collision. Can you please anybody close the door? So you didn't use the channel, I didn't use it. You got what I'm saying? Anyway. So for multiple access control, we're gonna use. So I'm gonna say it again because hopefully you are not confused about what I'm saying. To allow multiple access, okay? So actually we can do, as I said here, you can divide the spectrum or into bands, and all of us can transmit at the same time without collision because everybody can use a different bands. Is that okay? The other approach, if you transmit, you can take the whole band, but only one computer can transmit at a time. This is the other way. Okay? So here, what I'm gonna do in this is all what this chapter is about. So in this chapter, I'm gonna teach a different ways that you see here for multiple access protocols. That's it. Okay. So in the very beginning, so first of all, I'm gonna classify them as follows. Number one, we have some protocols, we call them random access protocols. We have controlled access protocols. We have channelization protocols. Under random access protocols, we have Aloha. I'm going to explain one protocol is called Aloha. I'm going to explain it. We have CSMA, and then we have two vectors of CSMA. Okay. Under controlled access protocol, I'm going to focus on token passing and polling. For channelization, we have something else. Okay. So first of all, for sure, I'm going to teach these 3 different protocols in details, but before I do that, I'm going to just make a very quick comparison between them, okay? So number 1, random access control, okay? So here is a channel is not divided. We don't divide the channels, okay? Nodes content. This content means they compete for the channel, okay? Collision are possible, so collision can happen, okay? But I'm going to try to reduce it. I'm going to try to reduce the collision as much as I can. Okay, like the second one, controlled access control. This one does not have collision, okay, because you actually here what you do some kind of reservation for the channel. It's not random. Okay, you reserve before you transmit. You have to reserve the channel. Nodes are scheduled and take turns. It's like they take turns to transmit. Okay. Is another one, the channelization or the channel partitioning, the last one. Okay, so here we divide the channel into small pieces, and then everybody is going to take one. So we're going to divide the channel either to time slot or some band frequency, and all of us can transmit at the same time, but you have to use your own band. Then that's why this one doesn't have a collision. This one we try to minimize the collision, but still it is possible. Yeah. Any questions? Anyway, I'm going to give you just a very, what it's still in the beginning, so I'm going to explain in details every one of these. Yeah. So let's take the attendance. Please 744. Don't share this code with anybody. I'm gonna call the names. If I find more people signed in, I'm gonna call the names. In the last section, I said that, and also someone shared the code with someone else, and I'm gonna see what I'm gonna do in this case. So 3744. Are you done? Don't share the code. Are you done? You are gonna make trouble to the other person because I don't know who shared the code, but at least I know the other person. Okay, so at least I was able to catch one case the previous section. Are you done? No, you are okay. No, it's 9. Yeah. So anyway, so let's start with the first one. The first one, we call it random access. And you should tell why we call it random. You will understand. Now, when I finish, you will understand what I mean by random access, okay? So under random access, as I told you, I'm going to teach CSMA. And the CSMA has 2 other versions. I'm going to variation. Also, I'm going to talk about Aloha, okay? Aloha. So all these schemes are distributed protocols. You understand what I mean by distributed? Distributed, that means there is no central unit. No one is controlling anything. It's just distributed between us. There is no central unit. You understand what I'm saying? So so all these protocols I'm going to teach. So no node is superior to another node, and no node is assigned to control to assign the control over another node. So there is no central unit. There is no someone that can control the protocol. Okay, we just run the protocol by ourselves. Okay, nodes transmit at full channel data rate without any prior coordination. So there is no prior coordination between us. Okay. Anyway, so here this protocol should tell how can we detect a collision, how can we recover from collision, and so on. Okay. Take a seat. So let's start with the first one. So the first one here, we call it Aloha. And under Aloha, we have two different types of Aloha. The first one, we call it unslotted. The second one is slotted. You can tell from the English name. Slotted means we have slot. We have slot, time slot. Okay? So slot here means we have time slot. Unslotted, it doesn't have time slot. Anyway, so I'm going to show you the difference and you will understand why you call it slotted. Do you have slots? Yes, we have slots. Okay? So you will see right now. So let's start with the first one. So the first protocol is called Aloha. We call it pure Aloha or unslotted Aloha. Pure or unslotted. We're going to do a minor change and then I'm going to call it slotted Aloha. Anyway, so let's start with the first one. How Aloha works. Aloha is very funny protocol. Very simple. Look how it works. Number one, you want to transmit? Go ahead and transmit immediately. Very easy, right? You want to transmit? Go ahead and transmit. Very simple, right? Very basic, very simple. You want to transmit? Okay, go ahead. Immediately transmit. Very simple, okay? But if you don't receive acknowledgement in two times the propagation time, you know the propagation time is the time for the signal to go and come back. So during this time, during a certain time, if I don't receive acknowledgement, that means that the data I transmitted are not delivered because of collision. I'm going to assume that it's because of collision. Okay, it may be because of noise, but anyway, because of collision. Okay, so here, if I don't receive acknowledgement, okay, during a certain time, so what I'm going to do, I'm going to wait for a random time. We call it back of period, and then I'm going to transmit again. Okay, I'm going to say it again. Say again. Number one, if you want to transmit, okay, go ahead, immediately transmit. This number one. Number two, if I don't receive acknowledgement during a certain time, I'm going to assume collision happens, okay, and then I have to retransmit. I have to retransmit. But I'm not going to retransmit immediately. I'm going to wait for a random time. We call it back of period, and then I'm going to transmit again. So if you look how it looks like here, number one, look at this one here. We're going to start the transmission at time T0. We are going to finish at T0 plus TFR. TFR is the time to transmit one frame. Okay, so here I start the transmission here, I finish here. TFR is the time to transmit one frame. Okay, and then I'm going to wait from here to here. I'm going to wait 2 TP. I'm going to wait 2 TP. Is that okay? From here to here. Okay. If I don't receive acknowledgement, I'm going to wait for a random time. We call it back of time. And then I'm going to try again, retransmit again. Any questions? Very simple, right? Any questions? So now, number one, why I have to wait? So you should understand what I mean by back of period. Back of period is a random time. I'm going to wait for this random time before I try again. You are not going to try immediately. Okay? Why? Can anyone guess why I have to wait for a random time before I read? Why you don't just retransmit immediately? Can anyone guess what happens if I don't make this one random? I just retransmit immediately. We're going to have repeated collision. Okay, so for example, I have data and you have data to transmit. I transmitted, you transmitted, collision happened. Is that okay? If we retransmit at the same time, we're going to have repeated collision. Repeated. So the main idea here, we're going to use, I'm going to use a random number here in order for so that nodes involved in collision, they are going to do retransmission at different times to avoid repeated collision. You understand what I'm saying? So already both of us made collision. Okay. So if we transmit again immediately, we're going to have repeated collisions. Okay. What happens? Every one of us are going to wait for a random time. Hopefully, after waiting for random time, Okay, we're gonna transmit at retransmit at different times. Still, it is possible to have repeated collision. It's still possible, but we're gonna reduce the chance for that. So, for example, as you see here, this computer is gonna send this frame here. So this frame, it's okay. There is no collision. This one is delivered. However, this frame collide with this frame, so there is a collision here. So collision happen here, okay? So everyone is gonna wait for a random time. So this one waited for random time, and this one waited for random time, but it may happen to have a collision again. This one here, there is no collision here, so this one is gonna be transmitted, okay? You should understand, I'm gonna repeat it again. When collision happens, we wasted the channel. You didn't transmit, I didn't transmit. Lose, everybody will lose. Okay? So one more thing I want you to understand. Collision, what I mean by collision is, if I want to transmit a frame this way, is that okay? Collision can be fully. Someone is going to transmit everything. Or it can be partially. So if you transmit in this period, so you are going to destroy this part of my frame. Still, the whole frame is gone. So you should understand, collision doesn't mean we have to transmit exactly at the same time. No, even if there is a small overlap, that means also a collision, because the data is going to be corrupted here. You understand what I'm saying? And you have to transmit everything again. Is that okay? So now, so let's see how this is one way to implement the idea of pure Aloha. Look how I'm gonna do it, okay? Here we have K. K means how many times you tried, how many times you failure. So transmitted, I failed. So I'm gonna try again. How many times is K? In the very beginning, K is equal to 0 because I didn't fail at all in the very beginning. Number one, I'm gonna send the frame. Number two, I'm gonna wait for double propagation time. Then I'm gonna see if I receive acknowledgement, success, congratulations, you did it, I'm done. If I don't receive acknowledgement, I'm gonna go this way. I'm gonna increase K. So failure is 1. I failed 1 time. Is that okay? And then I'm gonna compare it. How many times you have to retransmit? How many times you have to retry? Should I retry 1 billion times? No. What happens is actually I put a limit. For example, I'm gonna put T maximum. If you transmit a frame and frame is not delivered, you have to try T maximum. For example, I think we usually use the number 15, but anyway you can put any other number. But here it's gonna be 15. That means I'm gonna retry 15 times. After 15 times, I'm gonna abort. I'm not gonna send to this frame. Okay, so there is a limit. Anyway, so if K is less than K maximum, I'm gonna come this way. As I told you, I'm gonna wait a random time here and then go back, try again. So here I'm gonna wait a random time and go back and repeat again. Here I'm telling you one way you can do this random number in different ways. This random time, you can do it in different ways. I'm gonna do it using this way, okay? So the way I'm gonna do it is, as you see here, number one, I'm gonna select a random number R between 0 and 2 to the power K minus 1. K, when K is equal 1, so I'm gonna select a number between 0 and 1. When K is equal to 2, so it's gonna be 0 or 1 or 2 or what, or 3. You get what I'm saying? So I'm gonna select a number. So that means you should understand the bigger key, K, as K increases, the space is gonna increase. So the random number is gonna increase. You get what I'm saying? Because the more I fail, I have to wait more time. Okay? If I fail, because the more you fail, that means the network is too busy. You have to wait more time. The network is too busy. You understand what I'm saying? So anyway, this is the way. Again, this is one way to do it. You can do it in different ways, but this is one way to do it. Okay. So here, every time I fail, I'm gonna make the space bigger. So here the space is 0 and 1. Here the space is 0, 1, 2, 3. I'm gonna select a random number in this set or this set. And then this is the waiting time. So the waiting time is gonna be the random number times propagation time or the random times frame time. You can use either one of them. You understand what I'm saying? So anyway, you can tell here what I did. The bigger K as you fill more, so that means R has to be bigger. That means the back of time is actually gonna TB is gonna be bigger. You have to wait more time. This is the main idea. You can implement it in different ways, but this is the way I did. Example, okay? So in this example, the more you fill, you are going to wait more. For example, in the beginning, I'm going to wait 1 millisecond when I fill one time. When it is 2 times, I'm going to wait 5 milliseconds. When I fill 3 times, I'm going to wait 10 milliseconds, and so on. Okay? Any questions? Okay. So just I give you example just to understand this idea more. For example, here we are using Aloha. We're assuming this is the cable we have, 600 kilometer, 600. Then I'm giving you the speed, propagation speed. So here, what you can do here, you can calculate the propagation time, TP, propagation time. And the propagation time here is going to be 2 milliseconds. So I'm going to divide the distance divided by the velocity. You are going to get, this is the propagation time, okay? This is the time for the signal to move from the beginning of the 600 to the end. So you have 600 meters. The time for the signal to move from here to here is actually 2 milliseconds, okay? And then I'm going to calculate the delay or the back of time, the random time back of time at different values of K. So number one, when K is equal to 1, so I'm going to select a random number from 0 to 1, and this random number, and I'm going to multiply it by TP. I'm going to multiply it by TP, and this will be my delay. That's exactly what I said here. What I said here, after you get R, you multiply it by TP or TF, any one of them. But for example, here I'm going to use TP. Okay. So that means if you select 0, you are going to wait 0 millisecond. But if you select 1, you are going to wait 2 milliseconds. So in this case, either you wait 0 or 2 milliseconds in this case. Okay, let's see the second case. In the second case, these are the numbers you have when K is equal to 2, either 0, 1, 2, 3. So I'm going to select a random number in this range, in this set. So that means if you select 0, I'm going to wait 0 millisecond or 2 milliseconds, because everyone here, I'm going to multiply it by 2, right? So 2 milliseconds, 4 milliseconds, 6 milliseconds. You can see the numbers are getting bigger. Also here, it's the same thing here. If K is equal to 3, so this is the range I have. I get, so everything, the more you fill, okay, the bigger the space, the bigger R, the bigger time you are going to wait. Any questions? Should understand here. Number one, how I calculated the random time. You should understand why we need a random time here. Why it's not deterministic number. It has to be random. Again, to avoid repeated collisions. Because collision already happened between two computers. Okay, so every one of them is going to wait a random time and then try again. Hopefully, we are going to select two different random numbers, 2 different times, okay, and to avoid collision. Any questions? There is something very important here, very, very important. You have to pay attention to me. We call it vulnerable time or vulnerability period or vulnerable time, okay? So vulnerable time means in order to make sure my transmission is collision-free, I have to make sure no one else will transmit in this time. This is what we call vulnerable time. So if anybody transmits during this time, collision is going to happen. So, okay, so let me explain better. Okay, so here I want to transmit. I want to transmit. This is, you know, this is the frame I want to transmit. The time from here to here is called TFR. The transmission time, the frame, the transmission time for the frame, TFR. Okay. In order to make sure no collision can happen, number one, I have to make sure no one is gonna transmit during this time, TFR. You agree with that, right? So no one is gonna transmit during this time, TFR. Also, I have to make sure no one has already started transmission TFR before it, to avoid any partial. So no transmission should happen during this period TFR, and also no transmission has already started TFR before it. Okay, like this one. This one already started before it. Okay, that's why the situation. This one is started after the situation. So that means the vulnerability period here. So in other words, let me see it in a different way. The other words, in order to make sure my transmission is collision free, I have to make sure no one transmitted in this period of time. No one else is going to use the channel during this period of time. That's what we call vulnerable time, which is two times the frame, the transmission time of the frame TFR. You understand it? Yes. لا معلش no one is waiting here. Here everything is running. If you want to transmit, there is no coordination. If you want to transmit, just go ahead and transmit, and I will transmit. Okay, so there is no you are not going to coordinate any time here. Okay, I am saying what I'm saying. In order to make sure my transmission is collision free, there should be, it's out of my control because we are not coordinating transmission. Random. You want to transmit. So, okay, so the only way I can make sure there is no collision is there should be no other transmission during the vulnerable time. Either, okay, you got how I calculated it? There should be no overlap. So no one should start from here to here. And also no one already started in the base, already started from here to here to avoid any overlap like this one. Okay. Any questions? Why this one is very important and you are telling us it's very important? I'm going to tell you why. Look here. By common sense, think about it, by common sense. The higher the vulnerability time, is it something, or is that good or bad? Or lower is good or bad? Vulnerable time, higher is good or bad? Lower is good or bad? Can anyone guess? Higher is good. Do you agree? Any other opinion? Okay. How I can tell if it's good or not? Okay. The higher this time is that I'm more likely other people are can transmit and cause collision or not. Okay. So the main point here, higher is bad, because as this time is longer, there is more chance other nodes are going to transmit. For example, I'm going to give you extreme example. If this one is 1 hour, for example, do you think no transmission in 1 hour? For sure, it's going to be too hard to assume no one else will transmit. Okay, but if this time is just 1 millisecond, yeah, it is more likely no transmission in one millisecond than 1 hour. You know what I'm saying? So you should understand, the smaller the time, for sure, it is more likely, right? No collision. Because the smaller the time, it's going to be more likely there is no other one transmission, so there is no collision, more likely. Again, there is nothing here is definite, right? Everything here is about likelihood. It's more likely, probability, because everything is random. There is no coordination here, okay? That means the smaller the time is, for sure, is better. Okay, so now I'm going to ask you a question right now. And this is very important question. Maybe, I'm not sure, maybe in a quiz, in exam, I'm going to, but it's an interesting question. Maybe I'm going to ask it, okay? So I shouldn't tell you what I'm going to ask about, but I'm trying to help you. You need to help yourself first. Anyway, so what I'm saying is, So now you can't enter, I'm sorry. So now what I'm saying here is I can ask you a question, frame size. So is that better if we have a frame size bigger? Is that better to increase the frame size, or it's better to have a small frame size? Why small?
small ممكن الوقت يعني مش هيحتاج وقت كتير
TFR is small.
Respect.
So here, TFR is the transmission times of a frame. So when the frame is small, so TFR is small. And when TFR is small, vulnerability period is going to be small. And the light is going to be less likely to have collisions. You understand what I'm saying? Okay. Anyway, so it's related to TFR, right? Transmission time of the frame. So the smaller the transmission time of the frame, and this happens when the frame is small. So the smaller the frame, is going to be smaller TFR, is going to be smaller vulnerability period, and the smaller vulnerability period, it means less collision, which is good. Any questions? Okay, I'm going to tell you something also here. This is what we call pure or unslotted Aloha. We have another one, we call it slotted. We have slots. Okay. So we did a minor change here to this idea. We did a minor change, but this minor change had a big impact. What is the minor change? The minor change is in pure Aloha. I'm telling you, if you want to transmit, go ahead immediately transmit. Okay. So what? But in slotted Aloha, here, no. I'm gonna tell you, we have slots, as you see here. We have slots here. Okay. All transmissions has to start from the beginning of a slot. For example, I want to transmit here. Can I transmit Aloha? Yes. Slotted Aloha? No, you can. You have to wait to the beginning of the coming slot. This is very small change, right? So one of them is telling you, if you want to transmit immediately. The other one is telling you, if you want to transmit, you have to wait. You have to wait to the beginning. Okay? It's a small change. Okay. Why it has a big impact? Because this small change is going to reduce the vulnerability period by half. So now the vulnerability period here is only TFR. It's not 2 times. In Aloha, it is 2 times. Here, I was able to reduce it into half, vulnerability period. Because I reduced the vulnerability period in half, collision is going to be much less, which is much better. But the question, why you reduced the vulnerability period into half? Because there is no partial overlap as we had before. Either we transmit at the same time fully, okay, or not. So in order to make sure my transmission is collision free, I have to make sure no one is going to transmit in this period. Okay, because no one is going to start before it, or no one is going to start after it, because it's not allowed. I'm not going to allow that. If you want to transmit, you have to transmit from here. Any question? You understand the difference between Aloha and the slotted Aloha? In slotted Aloha, I was able to reduce the vulnerability period by half, right? By just making sure we have to transmit from here to the slot during a certain slots. Okay, but for sure that is not for free. Yes, I improved the collision. It's much less collision because I was able to reduce the vulnerability period, but nothing is for free. Two things here. Number one, if you want to transmit, you have to wait. This is number one. We didn't have this one before. So you have to wait, delay. Number two, we have to be synchronized. All computers, somehow, there should be a protocol, there should be a way so that all of us should have time synchronization. But all of us have the same time. Any questions? very important to understand. Number one, what is the vulnerability period or vulnerable time? What is this? What this time is? You should understand. Bigger the time is better, or smaller is better, right? You should understand the difference between pure Aloha and slotted Aloha. It's everything is the same, but one of them is gonna transmit immediately. The other one, you can transmit at any time. But for slotted Aloha, no. You have to transmit at the beginning of a slot. Okay. Anyway, then I have a very simple example here. I give you the frame size. For example, we have 200 bit frames, okay, on a shared channel, and the channel is 200 kilobit per second. And then I'm asking you, what is the requirement to make sure this frame is collision free? You know the requirement. It means there is no collision during the time 2 times 2 FR, because this is pure Aloha. Okay, 2 times 2 TFR. So all what you have to do, just you need to calculate the transmission time for a frame. And the transmission time for a frame is actually here the number of bits divided by bit rate. How many bits per second? Okay, so I already give you the bit rate. This is, I'm going to transmit 200 kilobit per second. Given this bit rate, I need to know the transmission time of a frame. So the transmission time is going to be 1 millisecond. Okay, 1 millisecond. This is TFR. That means, and so the requirement is, if I want to make sure there is no collision, I have to make sure there is no transmission during the vulnerability period, which 2 times 1, 2 milliseconds. No one else should transmit during this time. Any questions? Okay, good. Now, we need to measure something we call it channel utilization, efficiency, or throughput. Okay. What this means? I'm going to tell you before I give you details what this means. You can tell from the English name, utilization of the channel. Okay. So if I calculate the utilization of the channel and I find the utilization of the channel is 70%, what it means? It means 70% of the time there was no collision, and 30% of the time there was collision and I lost. That's why you call utilization. So I was not able to utilize the channel. I didn't use it 30% of the time. You understand what I'm saying? So that's what we call it channel utilization. So the higher the utilization is better. Okay. So, and how I can achieve higher utilization? There should be lower collision. Because normal utilization 100%. I have a channel. I have to use it 100% of the time. But because of collision, you are going to use it 50%, 30%, 70% of the time. As the other times, no one used it because of collision. That okay? Anyway, so now I want to calculate this channel utilization. You should understand what channel utilization means. Bigger is better, bigger is better or not. So now this is the formula we have here. So the formula is, as you see here, this is for pure Aloha. We have S equal G times e to the power negative 2G. S is actually the channel utilization. I can call it efficiency. I can call it throughput. It's the same thing. Okay. It's going to reflect how much collision you have. Okay. So now, if you have zero collision, this one should be 100% or 1. Anyway, so, but what is G? What is G here? Actually, G is what we call, G is actually the average number of frame transmission during one time frame TFR. Average number. How many on average, how many transmissions you have during this time frame TFR? On average. When I say average, that means this can be a fraction, like 1.2 to 2.7. Yet it is number of frames, but it can be a fraction because it's average. Okay. So what G is telling us, so what is, again, you are telling this average. So when this average increase, what it means? When it is less, what it means? When this average increase, that means the computers are transmitting too much data. right? Too much data transmitted, right? They are hungry, they are transmitting. You know what I'm saying? But a smaller G, that means the load, the transmission is less. We have less transmission from the computer. That's why actually G should equal N times speed. N is the number of computers. The more computers we have, the more G, the more load, the more transmission we have. You got what I'm saying? P is actually the probability I not transmit. The probability, or how much data you are going to transmit, the probability you are going to transmit. Okay. So again, G, you can understand G as the load. How much data transmitted, the load. I'm gonna measure the load or how much data the nodes are transmitting by calculating the average number of transmission during this time. Average number of transmission during this time. Okay. And this one depends on two things, not only one thing. It depends on two things. Number one, how many computers you have. The more computers you have, right, it's gonna be the more computer you have, the more G, right? You can have more transmission. Okay? Or also it depends on, not only that, it depends on these computers. Maybe you have too many computers, but they don't transmit too much data, right? So that's why also depends on P. P is the probability they transmit, right? Do they active in transmission or not, right? Anyway, so now we have G, okay? So I'm gonna do something interesting now here. So this one, you can call it the load. This is the load, how much transmission we have, or actually to be more accurate, the average number of frame transmission during this time, TFR. Anyway, so now I'm gonna do something interesting now. Okay, so what I'm gonna do, I'm gonna draw a figure. In this figure, x-axis is gonna be G, and S, I'm gonna put S here and see how the figure looks like. Okay, so this is the figure how it looks like. Okay, for pure ALUHA, again, this is G. G is the load, and this is S. So as you see in the very beginning, let me use a different color. In the very beginning, as you see, as we increase the transmission, robot is increasing. Yeah, because you're increasing the transmission in the very beginning, right? You are using the channel. So that's why the utilization is increasing. However, at a certain point, we found it's going to go back until it is zero. Why? Why you want back? It was supposed to continue. Why you want it down this one? Simply because of collision. So collision started. And the utilization started, or the throughput. Until it is, you know what zero means? It means 100% of the 100% collision. So it's like the network is not connected. You don't have a network. Everybody is transmitting. You did all the time. You have collision. You got what I'm saying? So that means, so you can tell from this one, ALUHA, pure ALUHA, the maximum you can get from pure ALUHA is 0.18, which is 18.4%. So bad. So you can only utilize 18% of the channel. 18%. That means 82% collision. 82% collision. 18% no collision. This is in pure ALUHA. Makes sense. Why? It's just simple. If you want to transmit, go ahead and transmit. Makes sense, right? It's very simple, right? However, in slotted ALUHA, as I told you, I did some improvement. Because of this improvement, we're again have the same formula here, but this formula instead of 2 here, you can see in the formula you have 2. Instead of 2, it's going to be 1 in slotted ALUHA because I reduced the vulnerability period. So now we have another one for slotted ALUHA here. Yeah, this one here. Okay. Now let's see what, and you can see improvement happened here. So what happens here? This is for slotted ALUHA. It's the same thing in the beginning. The more you transmit, the more throughput you have. At a certain point, we start to decrease. Why you started to decrease here? Because the effect of collision. You started to have collisions here. You have too much transmission. Remember, when I increase x-axis, that means you have too much transmission. You have too much transmission, but actually none of them or very few of them was without collision, okay, was useful, okay? So this one can tell you how much are useful, okay? That means slotted Aloha was able to improve the maximum from 18% to 36%, which is still bad. 36% means 1/3 of the time. That means if I transmit 900 frames, I'm gonna get only 300 delivered here in the best scenario. 1/3, 36%. Is that okay? Anyway, so okay, I think that's enough for today. I'm gonna continue next time. Okay, thanks.